Hello everyone, welcome to the lecture series of Computer Organization and Advanced Microprocessors. In this lecture number 32, we'll learn about the microprocessors in detail. In this lecture, we'll see that how many different types of microprocessors are available and what are the difference between all of them. So let's start. Based on the different parameters, total 4 different types of microprocessors are available. One we call them microcontrollers, then second is a RISC and CISC, then we have scalar and superscalar, and the last one is a vector and array. So these are the different types of microprocessors, and all are categorized based on their use and the technology. Before we go in the detail of the different types of microprocessors, first let's define the term microprocessor. We have already studied about the microprocessors, right? But let's see that how we define. So basically it's an electronic component that is used by a computer to do its work. If you remember in the very first lecture, we learned about the what is microprocessor, and of course and also we referred one or two videos for this, right? So microprocessor is an electronic component that is used by computer. It's a central processing unit on a single integrated chip or integrated circuit chip containing millions of very small components including transistors, resistors and diodes that work together and they perform some specific task, right? In the IC chapter of the integrated circuit, we learned about this, that how transistors are incorporated on the IC, remember? So this is the microprocessor definition, and it executes and manages the logical instruction passed on its. We know that when we talk about the microprocessor, the main job of the microprocessor is to execute some instruction, but alone it cannot do that. So we have different other components like transistor, resistors, diodes are there, buses are there, so many components are there, and all together work on some specific instruction, right? And they manage and execute all the logical instructions whatever we pass to it. So this is about the microprocessor. First, let's see that how microprocessors are classified. So, for there are certain parameters for that. So, the very first parameter is a technology. So, based on the technology, we have actually basically three different technology we normally use in the manufacturing of this microprocessor. Normally, microprocessors are designed by the semiconductor technology only, and the semiconductor technologies are nothing but the TTL, then we have CMOS, and then we have ECL, right? Already we have studied this all three in the logic family, not in detail, but we know that these are the technologies which we use in the manufacturing of the microprocessor, right? So the very first classification or very first category, that is the based on the technology you can categorize the microprocessors. So TTL, that is transistor logic, then CMOS is complementary metal oxide semiconductor, and the third one is the ECL, that is the emitter coupled logic. So after the based on the technology, we have word length. The second category is a word length. So based on the word length you can categorize the microprocessors. Like if you must have heard that this is 16-bit processor, this is 32-bit processor, I have a 64-bit processor. So that is the word length. Word length means that processor can execute this much of word length in one cycle. So that's why we call it a word length. So based on word length we have different categories like 4-bit micro, it's very old actually, 4-bit, 8-bit, 16-bit, 32-bit, and the latest one is a 64-bit, right? So this is the second category. Then the third is the based on the instruction set. Based on the instruction set, this we will see in little bit detail in next slide, but just for right now, based on the instruction set, there are two different instruction set types. The one set is a RISC, we call it a RISC, that is reduced instruction set computer, and the second is a CISC, that is complex instruction set computer. What is RISC, what is CISC, that we see in the RISC CISC uh, uh, topic, right? So this is the third category. Then we have based on the bandwidth. Yes, of course, we have already studied about the bandwidth, right? So the number of bits processed by the processor in a single instruction in a given clock time, that we call the bandwidth. So of course the bandwidth of the processor may vary from processor to processor, right? So based on the bandwidth as well, you can categorize the processors. And the last class category is the clock speed. So if you must have heard that 15,000 megahertz, 6,000 megahertz, 2,000 megahertz, right? So what is this? This is the clock speed. That clock speed determines that how many instructions a processor can process in one cycle. Let's say your processor can perform 1 million instructions, so the clock speed is a 1 million, right? So these are the different classifications for the microprocessor based on technology, word length, instruction set, bandwidth, and the clock speed. Now let's start with the different types of microprocessor. The first one is a microcontroller. What is microcontroller? See, microcontroller is a type of a microprocessor only, but it is designed to perform some specific task. Just like your calculator, your remote control, right? Your microwave, your washing machine, everything is automatic, right? When you press some particular keys, it performs that way, right? So there are the microcontroller. So the microcontroller is a compact IC, is nothing but the compact IC designed to govern a specific operation in an embedded system, right? So your calculator or your microwave or oven, your now we have smart fridge as well, right? So fridge you have. So all these are the examples in which you can find the microcontroller, and all have some specific task, specific operation to perform, and so we call it a then that we call the microcontroller. A typical microcontroller normally includes a processor, memory, and input-output peripherals. Let's understand this point. Let's talk about the remote control, right? Your TV remote control. So of course there in that remote control you can find the small microcontroller, and the main operation of that microcontroller is to control the TV, right? So in that microcontroller, inside your remote, okay, let me draw this. Okay, see, let's say that this is your remote control, right? This is your remote where you can find different channel numbers, and different channel numbers along with the volume button is there, and then some channel button is there, and so many other things are there, right? Okay, so inside this you can find a small microcontroller. You can find a small microcontroller. This is just a small microcontroller you can find. Now this is a special microcontroller. Why? Because it is embedded with what? Embedded with this remote control. Now the specific task of, or a specific job of this microcontroller is to control the TV, right? From these buttons you can change the channels, from these buttons you can change the volume, right? So this microcontroller must have a processor, right? Because when you press any key, let's say you are pressing this button, means you are giving the input. You are giving the input, and based on your input this microcontroller will perform task. Like this is the first number, one number channel, so it will automatically, it will change the channel, it will switch to the channel number 1, right? So of course, if because we have a processor inside this microcontroller, that's why we can perform this job, right? Okay, now next thing, memory. uh, you must be knowing that you can store the language, or also you can store your favorite channels and like that. So how your remote control or a remote remember this? Because inside the remote control there is a microcontroller, and that microcontroller contains the memory, right? So these are the components. And of course input output peripherals, yeah, sometimes you can find the input output peripherals always, because in this remote control you have in this remote, on this remote you have different keys, right? So these are nothing but the input, right? These are nothing but the input, and all these pins must be connected with this microcontroller, right? So this is the input, and output means if you have seen that in front of, okay, okay, in front of the remote control you can find the small bulb, small light, right, rays, right, and through which you can change the channel. That is nothing but the output, right? Because when you press some particular button on the remote control, that is the input, and that pressed button sends some signals through that light, through that bulb to the television, and so you can change the channel. So this is how your remote actually works along with the microcontroller. That is only because of the microcontroller, right? So this is about the microcontroller. The second type is a RISC and the CISC. So what is the difference? So RISC and CISC. RISC stands for Reduced Instruction Set Computer. What is the full form for RISC? RISC stands for Reduced Instruction Set Computer, while CISC stands for Complexed. CISC stands for Complexed Instruction Set Computer. Now let's understand it. See, if you have a more space, right, it means you can easily organize the things. But if you have a smaller space, in that case you need to, because you have the same data, in that case you need to arrange all the stuffs in a small area. It means it becomes a little bit complex. See this, here we have the image. You can see in the image that CISC, you can find that we have 1, 2 and 3 storage. How many storage we have 3 storage, or a 3 registers. Because I have only 3 registers but the amount of data is same, it means that I have to arrange my data. I have to input my data in such a manner. I have to manage my data in such a manner so I can keep all the data in these 3 registers. While so it becomes little bit complex, right? You can see this. But if I have 1, 2, 3, 4, 5, if I have 5 registers but the amount of data is same, that I can easily bifurcate the things, right? So it's very simple. Also you can understand this thing by, let's say that here we have a cupboard. We have a cupboard, right? And in this cupboard you have only two partitions, or two sections. So let's say here you can put your all the stationery stuff, and here you can put your all the clothes and everything, right? But suppose among the stationery, suppose you want some particular book or some particular pen, or from the clothes section, suppose you want to you are suppose searching for some jeans or something. So it becomes little bit difficult because you have a single area and all the stuffs are there. But instead of that, how if you have, let's say here I have 4 different sections, and here also I have 4 different sections. Now yes, I can put my jeans over here, then shirts over here, right? And in a stationery, let's say my books are here, my old pens are here. So in this case it is little bit easy. And the similar case with the CISC and the RISC. The RISC has larger number of registers, means comparatively more registers you can find, registers and the cache memory both, and few instruction type, it follows some basic instruction type only. While in a CISC you have relatively few registers. Relatively means relatively relative to the RISC. And extensive instruction means more instructions you need, because see, when you have limited area, in that case you need to give more instruction, right? Go up, go there, do this, do this, that's why. But if you have more storage, then you just need to say go to the first section, that's it, right? So this is the basic difference between the CISC and the RISC. In a RISC you can find the more number of registers in cache memory, but few instructions type, while in a CISC you have a relatively few registers and extensive instruction set you can find. So this is about the RISC and CISC. Based on the working style of the processor, here we have different four types: scalar processor, vector processors, then we have a superscalar processor and an array processor. Let's understand what is the meaning of the working style. What is the meaning of the working style? Let's understand this with one example. Let's say that there are three or four people we have. One is a 15-year boy, 15-year student, he is a student. Then we have 30 years of one person and he is an engineer, software engineer. Then one person is there, age is a 50 and he is a scientist. He is a scientist. Scientist. And one more person we have, let's say the same age, no worries, let's say 50, and he is a doctor, right? One more thing, let's say 45 age and he is a teacher. So one is a teacher, one is a student, one is a software engineer, one is a scientist, and one is a doctor. Can you suggest same configuration, same computer for all these five people? Can you suggest? No, we can't, because all have different need. All have different need, and based on that we decide or we suggest the computer. So based on the working style, that what is the actual working model, or what is the actual configuration and how your processor work, based on that we have four different categories or four different types of processors. Scalar, okay, see, scalar, then we have vector, then we have superscalar, and the last one is an array processor. We will see what is the difference between all these four processors and what are the actual meaning of these processors. But this is the idea behind the working style of a processor, right? Because how your processor works. See, if we talk about the scientist and if we talk about the student, see, suppose I have a computer. These are the two computers. This computer can perform, just for sake of understanding, let's say that this processor performs 1,000 instructions per second. Let's say this is just a rough scenario, instruction per second. Can scientists use the same computer? No, not possible, because scientists needs a fast processing, right? Because it has a huge amount of data. So this is not his cup of tea, and so he needs something more powerful, high-end computer, we can say, right? So this type of, or how your computer works, and based on that we have four different types of processor. That we call the working style. The very first processor is a scalar processor. What is the meaning of scalar processor? The meaning of the scalar processor is a processor that performs computation on one number, or a set of data, and one instruction at a time. Means suppose you say, or if you give the more instruction, more data at the same time, your system will not work if it's a scalar processor, right? Means scalar type processor can only perform one operation, one instruction on one data at a time. It is also known as the SISD, that is the single instruction single data. So we can say that this is very basic type of system, right? And here we have one example, like suppose I want to perform a1 plus b1 is equal to c1, or like that. Suppose these are the operation. So this processor can perform all the instructions one by one by one. It cannot go like all the three operations together, and so we call the scalar. So in short, if you want to remember, we can say scalar means one number or a one set of data and one instruction at a time, one instruction at a time, and that is the scalar processor. The second type is a vector processor. What is the meaning of what is vector processor? So it is a processor that is able to process sequence of data. Means I have n number of data with a single instruction. Means only applying single instruction, I can work on multiple data or a sequence of data. So that is the vector processor. And a vector is a linear array of operands of the same data type. If you have studied well the C programming, immediately something will come to your mind that can you relate this thing with the array? Remember, because see, if you have a one or a two numbers, then it's fine that you can take two variables. But suppose you want to perform operation on 100 or 1,000 data. In that case, we use array, right? So this is the array type, we can say, and that's why we call it a linear array of operands of the same data type. And array, and for the array, the same definition we have. What is array? Array is a, what we call array? Array is a group of elements with the same data type, right? Same data type. Okay, here we have an example. If you can see that here we have array of a1, a2, a3, a4. This is my first array. Then second is a b array, b1, b2, b3 and b4. Now I want to perform addition operation. See, just see this. What we are doing? Sequence of data, right? Sequence of data. Okay, we have a sequence a2 to a4 and b1 to before we have a sequence. Single instruction means you need a single instruction for multiple data. Okay, you have just given a single instruction that go and perform the addition operation. That's it. Whatever the answer you get, that's not the right time. This is not the concern right now. But what we need to understand, that the vector processor can perform uh, single operation on sequence of data by only applying the single instruction. And this vector is nothing but the linear array of operands. See, these are the operands, right? And these are the linear array. But the condition is everything should be of the same data type, right? So this type of processor, we call them vector processor. Next we have a superscalar. What is the meaning of superscalar computer? Remember the scalar? In scalar, what was there? One data and the one instruction, right? But here in a superscalar, it executes more than one instruction. See, remember. See, more than one instruction. Of course, it's a superscalar, so the capacity of this processor must be high. So more than one instruction during a clock cycle, whatever the time it is. One second you can consider, 1 microsecond you can consider, 1 nanosecond you can consider. So during a single cycle, it can execute more than one instruction. But how it will perform that? By simultaneously dispatching, because it has a multiple instruction, right? What it will do, it will dispatch simultaneously all the instructions, multiple instruction, to the different execution units on the processor. Let's say I have a multi-core system. In that case, see, we know instruction cycle, right? So instruction fetch unit, here we have the instruction fetch unit, and this operand fetch unit, this operand fetch unit will have all the instructions. Now let's say, suppose I have three 3 plus 5 one instruction, then one instruction is, let's say NO1 is greater than NO2, and let's say the third instruction is A is not equal to B. Suppose I have these three different instructions. So what this unit will do, this unit, because I have multiple instructions, see, first instruction, second instruction, and the third instruction. Now this unit will give all the instruction to the simultaneously. So see, it is giving all the instruction to different processors, ALU1, then ALU2, then ALU3, everything. And now all the processors will perform all the operations in parallel, and so we call it a superscalar. We call it a superscalar, right? Because it can perform, since this is the superscalar, because it can perform more than one instruction in a single clock cycle, and simultaneously it dispatching the multiple instruction to the different execution units on the processor, right? We have already studied about the write back, right? So write back means, what is the meaning of write back? Yeah, write back means first it will write in the cache, and after that it will perform the operation, after that it will write in the RAM, it will update the RAM. So this is about the superscalar processor. The last one is an array processor. So what is array processor? Array processor normally contains several processing elements that we call the PE. PE means the processing elements. What are the processing elements that we see? And their job is to operate in a parallel mode under a single unit. You will have a single unit, and in this single unit you will have a multiple processing element, and all this work together in a parallel mode, means everything will go in a parallel mode. And this PE is an ALU. This PE is an ALU with register and local memory. See, here you have ALU unit which contains registers as well as local memory, means ALU has its own registers and local memory. So here you can see in the image that some data is going to the ALU1, this ALU1 is going to the ALU2, and some other data is also coming to the ALU2, but still it can perform the operation. The similar way, some data is going to the ALU3, some data is going to ALU4, and ALU3 also requires the ALU4. So all this work will be done in a parallel mode. Why it can perform all these things? Because these ALUs have their own registers and the local memory, right? So this is about the array processor. Now our next topic is a BIU and EU, that is the bus interface unit and the execution unit. See, inside the processor, now we know that there are so many different components, buses are there, so many things are, so many elements are there, right? But how this bus interface unit and actual your execution unit work together, that we will see here. Okay, so here we have a diagram of BIU and EU, that how this both the units work together. So now let's understand that how they work together. Okay. So see, this is your BIU, that is your bus interface unit, and here you have your execution unit, right? This bus interface unit is nothing but your cables and everything, but this bus interface contains your all the segment registers, you can find in the BIU side, also external buses and instruction queue. So these are the three portion, normally we call them together the BIU. While in the execution unit you can find your flag registers, then your ALU, then some temporary registers must be there, some internal bus, and data registers, pointer registers, and index registers. So the group of all these units, we call them the execution unit, right? So how all this work together, let's see. First what happened, first you can find the instructions, right? This is the instruction queue. Now From where instruction will come? It will come from the bus control logic, and this is the external bus. See this arrow, this must be associated or the connected with the other input output devices. Now this instructions, I have instruction queue. Now instruction will go to the ALU depends that what is the actual job of the or what is the actual demand of the instruction. Based on first instruction will go to the ALU. Now depending on the execution, depending on the operation, it will set the flag. Suppose it requires some temporary register to store the value because your memory is busy. In that case, it will send that data to the temporary registers. Suppose it is not that, in that case, it will go to the internal bus. Through the internal bus, it will set the different registers. All the registers, index registers, pointer registers, and data registers. So depending on the depending on the instruction, it will set the values of all these registers, right? It solely depends that what is the actually instruction. Then after that, it might be possible that instruction directly go to the internal bus, and it can work with the this registers directly without the intervention of the ALU. It might be possible. Now this internal bus and your segment registers are connected with each other. So they normally passes the data, and this segment registers finally will go to the bus control logic, and it will go to the output device or a output socket. So this is how your execution unit and bus interface unit work together. So let's see some points about the BIU and EU. So basically this bus interface unit and execution unit are architectures. Both are the architectures that support the pipelining. What is the meaning of pipelining? The meaning of the pipelining is all all the units or all the components are connected together, and they work together in such a way that one can pass the data to any component, right? That we call the pipelining. Then basic, normally three phases are there. First it fetch the data, then it decode the instruction and execute the instruction, right? Normally any instruction when processor receive, first it fetch that instruction and decode it means it will find that how many operands are there, how many operators are there, and then it will execute that. So basically three phases. The major reason for this division, reason we have seen already, right, that there are two different divisions. BIU is one division and execution unit is another division. So the major reason for this division is to increase processing speed of processor. As we have seen in the previous image or previous slide, that if you have noticed this thing, see, when from execution unit, you can see two different arrows are there, right? One goes to the ALU and one directly goes to the internal bus. So here we can make sure that if there is no requirement of the ALU, in that case directly instruction can go to the internal bus, and that's why we can say that it can increase the speed. Then BIU has to interact with the memory. We have already seen this, that BIU normally interact with the memory and IO devices to fetch the instruction and data required by the EU. And normally execution unit is responsible for the executing the instruction of the program and to carry out the required processing that it can get from the all the registers, ALU, temporary registers, and everything. So this is why we need this partition, this division, BIU and the EU. So it was all about the different types of microprocessors and the division of the BIU and EU. So we'll see more in the next lecture. Till then, happy learning. Thank you.